So again, we're going to have our quiz on monatomic ions. Those are the ions you can figure out their charge from the position on the periodic table. And then you can go when you're done with the quiz. But we've got a couple of things to talk about before then, of course, and I'll review if you would like. So the first thing I want to point out to you is sorting the polyatomic ions. So this is part 2 of the sorting ions stuff that we started last week. And that should have popped into your classwork. Here. It looks very similar to the paper from last week, except it says, what are polyatomic ions? So you need to do the definition, and then there's a very small space for positives, right? Because almost all of them are anions. And it's the same process. You're going to use that same document you got last week. Common, monatomic, and polyatomic ions. And the point of this is to get you to normally handwrite them. If you want to type them, that's fine. You can also do it on a piece of paper and then upload a picture to the document to get full credit too. I just want to remind you about that. Remember, they have charges. Ions have charges. So I'm trying to get you to focus on the charge and put them into the correct charge box. And to know if it's a polyatomic, you need to look for more than one capital letter. Not more than one letter, 2 or more capitals. So for example, hydrogen just has 1 letter, so that's easy. That's monatomic, right? Nitrogen, hydrogen, and for nitrogen, H for hydrogen, with 4 hydrogens and a +1 charge, that's a polyatomic. So that would go into this +1 box. You'd write the formula and the name. Okay? The next one on the list, of course, is lithium. That's 2 letters, but that's the symbol for the element lithium. It's 1 kind of atom, so that's not going to go in polyatomics. Okay? The next polyatomic is number 25, hydronium. That also goes in the +1 box. And that's the end of the cations that are polyatomic. Okay? After hydronium, there's a couple of more monatomics. Here is OH, big O, big H. That's the hydroxide ion. That's going to go in the -1 box or the 1- box. Remember, the 1's not necessary. I include it so you are more likely to see the negative charge and stuff, but normally we don't write it. Write out the formulas. And then cyanide's another -1. Oxide, sulfide, nitride are all monatomic. There's only 1 capital letter. And then from 36 on through, they're all polys, except, there's always an exception in here, isn't there? Phosphide. I put that in by hand because it got left off of this list for some reason from Scientific. So that is most of what you'll be doing for tomorrow's assignment. Obviously, you can get ahead of a little short video at puzzle that I'm going to post tomorrow on ionic compounds for you to do. As your attendance for tomorrow, that'll be due tomorrow. And yeah, another thing that you'll see in your classwork feed, it's going to be confusing. Don't freak out. This is not due until Friday. We're going to go through this on during class on Thursday. I put that into the first period feed and we ran out of time because of the quiz. So I wanted everybody to have it, but there's no reason for you to do anything here. We're going to do this together, except for the questions at the end. But we'll go through the demonstration together, okay? So it's in there. Don't worry about it. Don't freak out about it. It is not. I'll explain it on Thursday, okay? So, questions on the calendar, on assignment stuff? Everybody okay so far? Video showed up. Oh, Aman is here, good. And how about Colin? Did Colin make it? Yep, okay, cool. Yay, everybody's here. All right, so If there's no questions on that stuff, let's talk about ionic compounds quickly. I'm going to do a short piece of the PowerPoint. I don't have a separate note sheet, so just take some notes down on a piece of paper, and we'll go from there to the quiz. So I'm back in chapter 7 again. Remember, we learned about ions and ion names, and I think it's important that you learn ion names when we're learning about ions. So that's why I went to chapter 9, because that's what this book does. But we're back here talking about ionic bonds now and electrons again. So this is a picture of someone harvesting salt from ocean water that's evaporating. And in some places, well, most of the world's population lives very close to an ocean. So this is one way to get your salt. But if you live farther inland, it's harder to get salt. And unless you're at the Great Salt Lake, I guess. But at any rate, this is a big pile of sodium chloride crystals, a whole bunch of big piles of it. And of course, salt is important for your body to function properly. Most Americans get way too much salt in their diet, and that causes high blood pressure problems. But evaporating seawater has more than just sodium chloride in it, but you can have sea salt, right? Lots of us buy sea salt. You basically have salt that is not pure sodium chloride. You have some other ions in there as well. Salt's used to de-ice roads and sidewalks. You've probably seen that this winter already. We don't use salt on the roads in California anymore because when the stormwater washes off and it gets into the soil on either side of the roads and it kills the plants. But back east, they still use it a lot, like what they're dealing with that huge storm that just hit them in the Northeast. They salt their roads quite a bit. In fact, I think I heard somebody, who's from New York City. Anyway, he said he had 100,000 tons of salt ready for the storm. I mean, I was like, wow, that's a lot of salt. All right. We harvest salt in this country, not just from the Great Salt Lake, but also in the oceans, but also there's caverns, there's caves in the Delta area around the Gulf Coast. So they actually go underground to get it. Anyway, little side. All right, what are ionic compounds? Well, a compound is two different, at least two, can be more, different elements stuck together, chemically bound. Okay, so they have chemical bonds holding them together. It's not just a mixture, it's two or more elements, atoms of two or more elements that are stuck together to make something new with very different properties, right? You saw sodium is a shiny silver metal, but the sodium ion is not. And chlorine is diatomic, and it is a toxic yellowish greenish gas, and it combines, these two things combine to make a white crystalline solid. So what do we have in ionic compounds? We have cations that have positive charges. We have anions that have negative charges. And that's what an ionic compound is. One thing that isn't brought up enough that I want to emphasize to you, cations, remember, those are the metals. Anions are the nonmetals, or groups of nonmetals if they're polyatomics. Okay. That when you look at an ionic compound, whether it's the formula or the name, the metal is named first. Right? NaCl, sodium's a metal. Okay? So the metal's first. What side is the metal on? On the name and the formula, it's on the left. That's where the metals live on the periodic table as well. The second part of the name is the nonmetal. Where do they live? On the right-hand side of the periodic table. Okay, so don't flip them. The positive one always comes first. The cations first. Of course, I say that, and then here's a picture from the book with the anion bromide coming from bromine, which is a brownish liquid at room temperature that turns into a gas. It's a diatomic, so there's two bromine atoms that stick together to make a bromine molecule. But they can come apart and make bromide ions. And aluminum is a shiny silver metal, as you know quite well. It has 3 valence electrons. It will lose. It doesn't just, those electrons don't just vanish. Where did they go? They went to bromines to make bromides. Okay, so each one of those 3 valence electrons from aluminum finds a home on a bromide ion. And so they stick together because opposites attract and create an ionic compound called aluminum bromide. Again, brown liquid, shiny silver metal, white solid. Almost all the common ionic compounds, they're white crystalline solids. It's really an identifying trait, actually. And we'll talk more about some other traits in a minute. All right, so here's a silly cartoon. So the make-believe teacher's in there asking why all the positive gentlemen are flying towards the window. And of course, positive sodium is attracted to negative chlorine. It's also attracted to bromine and fluorine, or fluoride and bromide and chloride ions. Remember, those anions change the ending. Okay, so electrostatic forces, just opposite charges, attract to form these bonds. What's really happening again is sodium with its 1 valence electron loses that electron. It actually donates it, gives it away, gets it ripped off by chlorine. When that happens, right, sodium has 1, it wants 8, it's easier to drop it. Chloride has 7, it wants 8, it can steal 1. So we end up with a sodium cation. Oops, I just covered up my positive. It has an octet, the highest energy level has 8. We end up with a chloride anion, which also now has, instead of 2 and 5, 7, it has 2 and 6, 8. It's octet. By exchanging the electron, both atoms become ions with charges, and both of them get their octet. So it's some terminology that you really need to get straight to make your life easier. When I say chemical formula, I'm talking about the letters and the subscripts that represent a compound. So chemical formula for water, H2O. You know that means there's 2 hydrogens and 1 oxygen. We don't write the 1, it's understood. Okay? We don't write H2O1, it's not necessary. Okay? If you go to the bother of writing an O, and make sure it's a big O for oxygen, it's there. Just like this one, calcium, a metal on the left. Chlorine, when it's a ion, it's chloride. And so the positive and the 2 negatives, right? This is a positive 2 because it's an alkaline earth metal. And each of those electrons goes to one of the chlorine atoms to make them chloride ions. But this is called a formula. Kind of jumping my guns here. This is a formula. Most of us think that, you know, if I said, what's the formula for a straight line? You'd go y equals mx plus b. That's really an equation, okay? That's an equation. There's an equal sign, there's a plus sign. That's an equation, not a formula. Even like, I do this all the time. What's the formula for density? D, m over v. No, that's the equation for calculating density, okay? So in science, we don't use the equal sign for chemical equations. We use arrows. Calcium with chlorine makes calcium chloride. And it forms, produces, makes, yields, generates. There's all sorts of words you could, you know, pose for the arrow, but we don't use equals. Okay, formula unit. Instead of calling them molecules for ionic compounds, we call them formula units. It's the lowest whole number ratio. Number ratio is a fraction of the ions in an ionic compound. So when I look at sodium chloride, it's a 1-to-1 ratio. One of these goes with one of these. When I look at calcium chloride, it's a 1-to-2 ratio. Only covalent compounds are supposed to be called molecules. I'm not going to get too upset about it, but we won't get to covalent compounds for a little bit. So the proper name for ionic compounds is formula unit. Really, they're just a bunch of positive and negative bits that stick together because opposites attract. All right, sodium chloride is a beautiful cubic crystal. When you get to look at it with a magnifying glass or a microscope, you can evaporate it slowly. You can set some aside on your kitchen windowsill if you want, and you will, if it evaporates slowly enough, the crystals will get very large and you'll be able to see it. I have some halite at school. I forgot to grab that. That I'll try to remember to show you again. But it's a alternating cube. It looks like a dice. So I'm going to show you this real quick. One of the fun things about science is we get toys. So I have a sodium chloride ionic compound magnetic toy. So those of you who like to play magnets, this is pretty fun. These little spheres, of course, are supposed to represent atoms or ions, and they are attracted only to the oppositely charged ions. So if I try to put the two green ones together, they won't stick. And that's because the green ones are supposed to be chlorine, and the blue ones on my model are supposed to be sodium. Remember, sodium's a metal, it loses, it makes a smaller, a smaller ion. Anyhow, lots of fun to play around with. So sodium chloride is a cubic crystal. There are other patterns that form, but this one is cubic. So on the sodium chloride, the chemical formula, NaCl, +1, -1, all done, 1-to-1 ratio. You could write hundreds of them and still be correct as long as they have equal numbers, but they don't. Okay, so 1-to-1 is the smallest, right? So like CaCl2 is a 1-to-2 ratio. That could be Ca2Cl4. That's the same proportions, but remember from your math class, right? Reduce that fraction. Okay, make it as simple as possible. All right, real quick, 3 properties of ionic compounds. First one I've already mentioned, they're crystalline solids at room temperature, almost all of them. I can't think of any that aren't crystalline solids at room temperature, but the book doesn't say all, so I think they're just hedging their bets. So big crystals, small crystals, they're still sodium chloride in their alternating pattern. The other thing I just want to mention really quickly is almost all of them. Do you remember the aluminum bromide at the beginning? That is still white. It's really strange. There are some crystalline solids, some of these ionic compounds that are colored, but not many. Copper chloride's one of them, the one that we used with the aluminum foil beginning of the year. There's some pinky red ones too, but not very many. Melting points. One very important thing to mention is that the melting point is very high. So we abbreviate melting point MP, boiling point BP. Kelvin temperature scale is the absolute 0 scale, so there are no negative numbers. So 0 Kelvin is absolute 0. And you add, excuse me, you take away 273 from this. So basically 800 Celsius is the melting point. Remember, 100 Celsius is the boiling point of water. 800 is a lot hotter. So it takes a very high temperature to melt, but you can melt salt. It's crazy. You can have liquid salt. you can also see that some of them are even higher. So boiling points, again, that's when a liquid becomes a gas. You can turn salt into a gas. Kind of crazy. So solids into liquids, that's melting. Liquids into gases, that's boiling. You guys know that. The last really cool thing about ionic compounds, when they're melted or when they're dissolved in water, they conduct electric current. And that's because when you put an ionic compound into water, it will dissociate. Not every single one of them, that's for sure. There are some that are very insoluble, but there are also quite a few that most of them are soluble. They dissociate, they come apart. What do they come apart into? The positive and negative bits. Okay? And those free moving charges then are able to conduct electric current. This is the video for tomorrow. This is humorous, but I'm just going to show you mine. One really important point is that even though ionic compounds have charged bits that they're made from, they are neutral. +1 and a -1, you know, adds up to 0. So there is no overall charge on an ionic compound, and they are not, they're not going to zap you when you touch them. So dry sodium chloride doesn't conduct. Dissolved sodium chloride, remember the AQ is for aqueous, I didn't mention that earlier, will. Okay. Melted sodium chloride also will. All right, and then just as a review and just as a reminder, each group or family has their own number of valence electrons. Remember, the transition metals are here. Group 1, alkali metals have 1. Group 2 have 2. Group 3 have 3. All of these are going to lose electrons and get their ionic charges correspondingly. So everybody here gets 1 dot for 1 valence electron. They lose it. They end up with an overall +1. 2, oops, that's 1, 2. 2 dots, they lose them. They end up with a +2 charge. Every element in this family, no exceptions. Groups 3, 3 dots, lose them. Okay? +3 charge. Group 4 has 4 valence electrons, but this isn't really true. Okay, and then even though you see that in tons of books, group 5 wants 3 more. Everybody's goal, remember, is to get an octet. So if we get electron, 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 this group will get 8 valence electrons and have a -3 charge. This group, group 6, has 6 to start with. 1, 2, 3, 4, 5, 6. 6 plus 2 more electrons from somebody else gives everybody in oxygen's family 8 valence electrons. All of the halogens have 7. They are super duper reactive because they just need 1 more valence electron to get their 8. Okay, and so they get a -1 charge, and of course the noble gases don't form don't form ions because they have their octet or 2. All right. Questions I can answer for you right now on the review? On anything I covered so far today.